Hey, welcome to another video. So in this video, we are finally going to graph some rational functions. We are going to do everything that we've learned about, but we haven't really put it together. And so that's what this is going to be about. We've learned all the little pieces. So we know how to do things like find a hole, find a vertical asymptote, find a horizontal asymptote, X-intercepts, Y-intercepts, but I've not shown you how to graph them. And there's a lot of cases here. And so we're going to get a lot of examples, but it's going to be a good video. So I'm going to give you the steps. We're going to go through about 6 examples. 5 of them are going to take a little while. One's going to be pretty quick. Then 2 examples of some special cases, special instances we can see. So we're going to get right into it. How we graph rational functions, I want to put in your head what the steps are in order to do this really accurately and as efficiently as possible. So a little bit of speed here, but accurate. So that's what we want. So the first thing that we're going to do is we're going to find some horizontal asymptotes, or well, there's only one, or an oblique asymptote, or just straight up end behavior. And it's going to be one of those 3 cases. So we're going to talk about finding those first. And the reason why is because if we factor first, well, then we have to go backwards to find that. So typically, your rational function doesn't come factored. That would be easiest to find your horizontal asymptote first in that case. Not too bad. We use our leading terms from the numerator to denominator, and we find it if one exists, or we do long division for oblique asymptote, or we just find straight up end behavior. So we're going to talk about that first. Then we're going to factor and find a vertical asymptote or asymptotes, or a hole if we have one. And we're going to find out whether that is multiplicity odd or even. That has to do with how our graph has to interact with our vertical asymptote. And if we have a hole, we're going to find out where that hole is in ordered pairs signifying where that exists. Or doesn't exist, I guess. So we're going to do that second. After that, the next two are pretty quick. We're going to use our numerator set equal to 0 to find X-intercepts. We're going to plug in 0 to find the Y-intercept. And then, kind of a special case, if we have a horizontal asymptote that is not 0, so a horizontal asymptote equaling 0, we wouldn't do this. That's what that little note says right there. But if we have a horizontal asymptote equal to a constant that's not 0, or an oblique asymptote, we have to check to see whether our graph intersects that. And so we set them equal and we try to solve it. If we run into some sort of nonsense statement mathematically, well, then it doesn't intersect. But sometimes these do intersect an oblique asymptote, that's a slant asymptote, or a horizontal asymptote that's not 0. Why don't we care about the 0? Well, if we set our function equal to a horizontal asymptote that equals 0, we're going to find X-intercepts, which was already done right there. So we really don't need to do that twice. This doesn't happen super often, but it can happen. After that, what we're going to do, we're going to make a number line that has all of our relevant points on it. All of our X-intercepts, all of our vertical asymptotes on the X-axis. That's what those things would do. We're going to make a number line that represents that X-axis. And then we're going to plug in some extra points. So for every interval that we have, we're going to evaluate something, and that's going to give us a much more precise look of our graph. We haven't done this in the past. We've been sketching. This is getting closer to graphing. It's still sort of sketching, but we're moving closer to that because we'll have a little bit more accuracy. After that, we're going to be ready to graph, and we're going to get right to it. So let's go ahead. Let's start. Again, I'm not really trying to teach you how to find a vertical asymptote. I'm just teaching you when you would do it. I'm not teaching you how to find a horizontal asymptote. I'm just showing you how you would check to see for an intersection and put it on your graph. So this is going to be quicker as far as my explanation of these concepts. We've already talked about them. You've already learned them. Trust that. Trust that you have that. We're just going to show what the pictures are as we graph them. So number one, the very first step that we're going to do, just to get a feel for how these steps work, is we're going to find the horizontal asymptote or oblique asymptote if those exist, or end behavior if they don't. And how we do that is from an unfactored form. It's a lot nicer to do that when it's not factored, because you don't have to do that sort of fake distribution and use your leading terms. We already have them. So that's what we do at first, so we don't have to factor and then sort of undo that. So when we take a look at it, our leading terms are x for the numerator and x squared for the denominator, which means that our end behavior is going to look like the ratio of those leading terms. And if you remember, what we do is we take those leading terms, we simplify it, we just think about what in the world that would do as x approaches positive infinity and as x approaches negative infinity. That's a limit idea. I showed that to you one time. Really, I'm not going to show it to you again. We're just going to be thinking through it. But really what we're doing is thinking about this. What happens to this function as this variable gets closer to this thing? And we do positive and negative infinity actually, but the idea is as x gets bigger and bigger and bigger, or smaller and smaller, not smaller negatively, so absolute value larger in both directions, what's happening to my function? Well, the 1 would not change, but that number is getting real big. Well, that means that this fraction is going to approach 0. This is the idea of end behavior. It's the same idea. It's always just end behavior, but the way that we refer to it can be a horizontal asymptote, an oblique asymptote, or sometimes we get like a quadratic look, or some other end behavior like even or odd. So in this case, when we have 1 over x and x is approaching infinity, if you ever have a variable on your denominator and a constant on your numerator, you're going to have a horizontal asymptote at 0, at y equals 0, and we're going to write that. So we're going to have a horizontal asymptote at y equals 0, and we're going to put that on a graph in just a little bit once we figure out the rest of our steps here. So that's our first step. We take our first terms, our leading terms, we put them in a ratio, and we think what's happening. Yes, there are sort of formulas, kind of quasi-formulas that says if you have a constant over a variable, you have a horizontal asymptote of 0. That's true, but I want you to understand why. I want you to go, yeah, that's 0. I want you to think, what happens when x gets really big? 1 stays the same, x gets really big, it's 0. The graph is going to get closer to 0 somehow. That's why that's there. So we have a horizontal asymptote at y equals 0. The second thing we're going to do is we're going to factor this entire polynomial. We're going to factor the numerator as much as we can. We're going to factor the denominator as much as we can. And so we get this x minus 1 over x minus 2 times x plus 2 due to that fact it's a difference of squares. And then we're going to start thinking about this in terms of, do we have a whole or a vertical asymptote? Do we have some sort of denominator issue that's causing that? And when we look at it, we see two factors on the denominator, both of which do not cancel with the numerator, otherwise we would have had a whole, and both of which would cause the denominator to be 0 at 2 and negative 2 respectively. So what those things are is those are vertical asymptotes. We learned about that. So I know that at x equals 2, now I'll do a little bit more work, I'll show it to you. X minus 2 and x plus 2 both equal 0. And we're just going to write a little bit about what that means. So we said if our denominator equals 0, we have these discontinuities, either a vertical asymptote or a whole. In this case, because our factors don't cancel, we've got some vertical asymptotes. We have 2 of them. And we also want to know what they are. We want to write what the multiplicity is. So we're thinking about it going, you know what? Because these come from factors that are 1 and 1 as far as their exponents are concerned, those have a multiplicity 1 each. That means they're both odd vertical asymptotes. So we're going to write that out. We're going to write a vertical asymptote and that it's odd. Vertical asymptote and again odd. It's going to be very important for us to see how our graph interacts with the vertical asymptote, whether we're, hopefully remember this, even would match up on both sides, go to the same infinities from both directions as we approach those asymptotes from either side. Odd is opposite, so odd, opposite somehow. We're going to see that bear out in our graph. So we've done our horizontal asymptote, we've got our vertical asymptotes, we've already listed them, our multiplicity was 1, so we just need to understand that that's odd and that's going to be opposite as far as our infinities go. On step number 3, we're going to find our x-intercepts. This is typically not all that bad. Once you have this factored, your numerator is going to tell you the factors that let this fraction equal 0, and that's exactly what our x-intercepts are, is when our function equals 0. So think about this. If our function is set equal to 0, so this whole thing set equal to 0, if our denominator equals 0, those are problems. We already did that. So the only place where the function can actually equal 0 is where the numerator equals 0. Also, I want to say at this point, it's real important for you to do these steps in order. And the reason why is because we don't really want to find an x-intercept before we've taken care of finding a whole. Why is that? Well, if we find an x-intercept before we've taken a hole, do you remember that the holes cancel out? So you'll find an x-intercept, and then later if you found your hole and you cancel them out, like, wait a minute, didn't I cancel my x-intercept? Yeah, kind of. That's why we cancel the hole factor and write down what that hole is before we do x-intercepts. So at this point, you should have taken care of the hole. You should have something that's simplified if possible. And then we just set our numerator equal to 0. It's the only part of the fraction that can actually let the function equal 0. So we look at it and go, all right, from this step, let's set our numerator, x minus 1, equal to 0. And x equals 1. That's our x-intercept. Oh, don't forget, this also has a multiplicity to it. So it's going to tell you whether it's a cross or a bounce. You know what? Maybe I'll draw it again up here. If we set that equal to 0, only the numerator has the opportunity, so we do that. But we also remember that x minus 1 is its own factor. That's where we're getting the x equals 1. That's where we understand that this has a exponent of 1, that's a multiplicity 1, that's an odd multiplicity. And when we talk about x-intercepts, that means that we're crossing the x-axis here. And that's about it. So that's the only x-intercept that we have to pay attention to because that's the only one that there is. So we're going to be crossing the x-axis at x equals 1. The next thing that we do, step number 4, we're going to go down, we're going to find our y-intercept. This one's pretty easy. You can do it anywhere in the function. You can do it at the very beginning. That's probably actually the easiest. You can do it here when it's factored. That's fine. You can do it here when it's simplified. Not a big deal. Anywhere you want to go, just plug in 0. Which also says that the hole does not affect, if you have one, does not affect the y-intercept. It doesn't matter where you plug that 0 in. It's honestly not that bad to do. So when we plug in 0 here or here, you'd get 0, 0, 0 minus 1 is negative 1. 0 minus 4 is negative 4. Negative 1 over negative 4 is 1/4. So when we evaluate, we just are evaluating x equals 0. Notice if you do it here, you'd still get negative 1, 0 minus 1. And here you get 0 minus 2, that's negative 2. 0 plus 2 is 2. Negative 2 times 2 is negative 4 still. You're basically getting the same thing. Negative 1 over negative 4 is still 1/4. It's still the same. So it doesn't really matter where you go. What does matter is after you do this, to put it accurately on your graph. We really don't want to make mistakes there. Now, you'll see I'm missing a step 5, and here's why. If you have a horizontal asymptote that equals 0, this step is irrelevant. If you don't have a horizontal asymptote or an oblique asymptote, this step is irrelevant. It doesn't matter. And so what we're going to check for is if we don't have a horizontal asymptote that equals 0 or end behavior that's not an oblique asymptote, we're going to check for an intersection. I said it I'm going to say it just one more time. If you were to go and set your function equal to 0 right now, so if you took your function right here or right there and you set it equal to 0, that's exactly what we have there. It would just give you x-intercepts again. You don't have to do that. But if the horizontal asymptote is not 0, you would need to do a step 5 here. In step 6, all we're going to do is we're going to take these important points that we found, put them on a number line, and plug in some additional values. So here's what we mean by that. We're going to take every vertical asymptote and every x-intercept, we're going to put them on that number line. What this does, it models the x-axis for us and lets us go straight to a graph pretty easily. So x equals negative 2, that's one of our vertical asymptotes. I'm going to put odd. Vertical asymptote odd. X equals 1. Remember, this is a number line. It's got to be in order. That's an x-intercept, so we're going to put cross. And by understanding the context, we understand that's a vertical asymptote. We're not really touching the x-axis here. It's giving me a vertical dotted line in which I'm going to interact with somehow. This is going to be an x-intercept. That's what the cross is. We are touching the x-axis and then crossing at that point. And then x equals 2 is our other vertical asymptote. That's also odd. Probably the most time-consuming thing that we're going to do is the next step. What we're going to do is we're going to evaluate, and the reason why is we want some pretty decent graphs. All of this stuff has to mesh together, like this horizontal asymptote and the vertical asymptotes and the X-intercept and this Y-intercept, they all have to work. So I'm going to show you how to sketch, and then I'm going to show you how to graph a little bit better. One way to graph versus sketch is to introduce a couple extra points. So for every interval, this is why we do this number line. For every interval, like this one, this one, this one, this one, plug in a value. Plug in something that's hopefully easy to evaluate into your function and find an ordered pair. You can do it anywhere. You can do it here from the original, you can do it from the factored, or if you simplify, you can do it from the simplified version of this. That's probably the easiest to do. So I'm going to evaluate for a few ordered pairs here. So we don't want to do 0 because we already have a Y-intercept. So something like -1. Something like 1.5. And something like 3. So here's what I got when I evaluated these. I evaluated -3 into my function here or here, and I got -4/5. I evaluated -1, and I got 2/3. 1.5, I got -2/7. 3, and I evaluated, I got 2/5. And you can use decimals, that's fine, but some of those are not going to be very nice decimals, like -2/7 is like -0.28 or something. So, and then 2/3 is 0.667. It's good enough for us, but just be aware that fractions are sometimes a little bit nicer. Now we're ready to graph and put everything together. So the way that we graph this is the same way that I put these steps in order for you. So number one thing we're going to do is we're going to understand our end behavior. In this case, our end behavior is a horizontal asymptote at y = 0. So we're just going to have a dotted line. Now I've mentioned this before, you've heard me mention it, that we have to check for an intersection of a horizontal asymptote. Keep this in mind. You can intersect a horizontal asymptote. That's why we have X-intercepts here. So we do cross this. It's not the same as a vertical asymptote. You can't ever touch that. But a horizontal asymptote or an oblique asymptote is something the graph can cross. So don't make that misconception. It's really common for students to go, wait a minute, now I'm crossing the x-axis. Yeah, that's fine. It's okay. What happens is we're thinking about x approaching positive infinity. That's way out there. That's not here. Okay, this is not even close to positive infinity. So things can happen within a finite region, then afterwards we approach an asymptote. So that's what's really happening. We're just going to show the dotted line at the ends of our x-axis. Then we're going to go ahead and we're going to plot our vertical asymptotes. We have 2 of them, -2 and 2. And we're also going to signify that these are odd. That's going to help us when we're graphing in just a moment, cue our brains into what's going on around them. So we're going to put odd and odd. Do you notice how I'm making lots of little notes to help myself? Like, do that. It's really hard to have all this in your head and get it right. It's a lot better to put little notes like, oh, that's odd. What I mean in my head right now is that this is either going to interact this way or this way, depending on how our points and how our graph is shaped. Same thing with that one. Then I'm going to put down our x-intercept. Our x-intercept is at x = 1, and I know it's a cross. So I know we're crossing there. Remember that I came up with something, that little dotted line, if it's a bounce, or we call that a touch sometimes, we're not going to use that, signifying we are crossing the x-axis. After that, what we're going to do is we're going to put our y-intercept. Our y-intercept is 0, 1/4. It's about there. We just want to make sure it's on the correct side of the x-axis, so that's positive. I want to make sure that I put that, not accidentally put it down here. A real hard time making the graph work if we did that. And now the last 2 steps. This, and you can probably see it, I'm going to talk about the difference between sketching and graphing. You're going to see that the sketching is quicker, but the graphing is going to really help you. We're getting closer to graphing by using some points. Here's the idea. If all of this stuff has to work together, there's really only one way that this graph can be shaped, And that is based on where your y-axis is in relation to your x-intercept, or y-intercept is in relation to your x, and here's why. You see, these have to have opposite infinities. So this way or this way. But if we trust that we have all the x-intercepts down, which we do, and that our y-intercept is accurate, which it is, and we found the vertical asymptotes and have their multiplicity correct, which we also do, and you have your horizontal asymptote, which we have, then this graph has to interact a certain way. So if there's no other x-intercepts, there is no way for our graph to come down anywhere in this range. We cannot do it in this interval. We can't do it. So because we have our y-intercept there, and we do not have any other x-intercepts here, it would have shown up. This graph has to do this. It must hit this from going from positive infinity, downward, hit it. It's got to go and cross here, we know cross, and therefore because it's a cross, we have to interact with this vertical asymptote going toward negative infinity. It's the only way this graph can look. Furthermore, because we have an odd vertical asymptote, this graph has to now come from up here. It can't cross the x-axis. We don't have any other x-intercepts. And it must interact with our horizontal asymptote. On this side, because this was from positive infinity and this is an odd vertical asymptote, the other part of this graph has to end this way. There's no x-intercepts, it cannot cross it, it has to interact with the horizontal asymptote and the vertical asymptote and the opposite because it was odd. That's a lot to think about right now. So that's the reason a lot of people like me use some points here. You see, if we put these points on, and say, hey, yeah, at -3, we got -4/5. -3 comma -4/5 is right about there. -1 comma 2, positive 2/3. Here's -1, there's 2/3. At 1.5, we got -2/7. 1.5, -2/7. And at 3, we got 2/5. It's like 0.4. By putting those extra points, do you see how it takes a lot of the, maybe not guesswork, because we weren't guessing about the sketch, but it gives you not only some more accuracy because you have some actual points, but it really shows you where this graph goes. Like there's no guessing about it now. That's why I'm going to encourage you to do that. Yes, it takes a lot of time, and I just wrote them up there. You have to take the time and evaluate on your function. Sometimes it's really nasty, but hopefully you see it's going to make a better graph for you. So now we have no guesswork. We have all of the x-intercepts down, we have all the vertical asymptotes, we have our horizontal asymptote, and we have our points. So we graph it. Trust that you found everything. Don't accidentally go, well, what if it does this? It doesn't, because it would cross the x-axis if it did. It can't. So our graph must look like that. It's got to look like that. There's no other way for this graph to interact with the x-axis and the vertical asymptotes other than what we've just shown. Because this is odd, I know that now I have an opposite infinity. Because this is odd, I know I have an opposite infinity. And we're still going through the points that we just found. We also have to interact with the horizontal asymptote. We know that we don't cross it because those guys would have been other x-intercepts and we didn't have any of those. So is it still a sketch? Yes, it is. It is still a sketch because we don't know exactly where this goes. We're kind of modeled pretty well. We have a lot more points than we would otherwise, but it's still sketching. It's closer to graphing because we're using some of those points. We also don't know exactly where like a point of inflection would be, or any sort of, and that's where we change concavity. It's a calculus 1 idea. We don't know exactly where that is. We find out in Calc 1. And so we're getting closer to that. We're getting much closer. So I hope that makes sense. This was the first example, just going through all of our steps here, unpacking the next 5 examples. We're going to talk about what happens when you don't have a horizontal asymptote that's 0, when it's some constant, or an oblique asymptote, if they intersect and where they don't, how to deal with a hole, and then how to go backwards on some graphs. Okay, here we go. We're going to get right into it and do another example. So As we move through, I'm not going to be pausing as much to explain some of the concepts we've already covered. The only times I'm going to stop and go a little bit slower is when we've done things, we're doing things we haven't done yet, such as our end behavior here. So I'm going to explain that a little bit when we get there, but this is mostly just to get things in your head so that this is all gelling together. So first thing we do, now we're going to look at this and go, hey, is there an end behavior? Yeah, what is it? End behavior takes the first two terms, so the numerator's leading term and the denominator's leading term, puts them in ratio, simplifies, says what it, and we get a picture of what it does. So we take our x to the fourth over x squared, those are our leading terms. We simplify, we get x squared, and then we think about what happens. So this right here, our numerator sort of outpaces our denominator. We get x squared when we simplify, and that says our end behavior should look like whatever that power function is. That power function is x squared. It is going to look like a parabola as x approaches positive and negative infinity. So our limit means as x gets bigger and bigger and bigger to positive and negative infinity, that function says take positive infinity, square it. Take negative infinity, square it. For you, positive infinity, square it, positive infinity, square it. You're going to get this parabola shape to it. That'll bear out when we graph this. So we know this is not a horizontal asymptote. We know it's not an oblique asymptote. This is just our standard end behavior. And we're going to draw a little picture of that. So x squared looks like a parabola with some things that happen in the middle. After that, step number 2, we're going to factor all of this. So when we do, notice the numerator is a power 4. It's also a difference of squares, so we just have to do it twice. So on our numerator, we can think of this as x squared minus 1 times x squared plus 1. Over our denominator is x minus 2 and x plus 2. It's a difference of squares. But that also factors again. So we can factor this as x minus 1, x plus 1. X squared plus 1 does not factor anymore. That's done. Over x minus 2, x plus 2. And now we're ready to find a vertical asymptote or a hole if we have one. So vertical asymptote says look at your denominator, look at the factors that are causing your denominator to equal to 0, write them down, and then see if you can cancel them. If you can, that factor created a hole for you. If you can't, that factor created a vertical asymptote, and then identify the multiplicity of that. So our denominator says, at x equals 2 and negative 2, we're going to have some issues. I always write down the factor from where I'm getting those. It's very, very easy when you have different exponents to confuse where that domain issue is coming from if you don't write down your factor. So I'm writing down x minus 2 equals 0. That way I can follow this back and say, oh, that had an exponent 1. I cannot cancel that. So this domain issue right there is causing a vertical asymptote, which has an odd multiplicity. So vertical asymptote odd. And the same thing happens here. This is coming from the factor x plus 2. I can't cancel it, so it's not a hole, it's a vertical asymptote, and it has a multiplicity 1 stemming from that exponent, and so that's also vertical asymptote odd. After we've done that, what we're going to do is we're going to take this factored form. We would have simplified if we could. That would have given us some holes we don't have. We're going to take our numerator and set our numerator equal to 0. The numerator is the only place that the function can actually equal 0. The denominator can't even equal 0. That's where we got our vertical asymptotes from. So on the numerator, we take, on this next step, step 3, we take our numerator, we set it equal to 0, and we solve it. Hopefully you notice it's nice to do it from here because after you've factored and simplified it, it's really easy to use a zero product property and say, if my numerator is equal to 0, it's already been factored. I'm going to set every factor equal to 0 and solve. So I'm going to set x minus 1 equal to 0, x plus 1 equals 0. This one I could, but it's not going to give me anything. X squared plus 1, you can't factor that anymore. That would give you some complex numbers. Since we're looking for actual x-intercepts, complex numbers don't help us here. If we did, though, if we set the equal to 0, we'd have to list out something like, this is no real solution, therefore there's no actual x-intercept. At least not from that factor. That's an irreducible quadratic. But the other two are very clearly solvable. So we can get 1, we can get -1, and we understand that because those factors have this power 1, that's an odd multiplicity, and that says those are going to be crosses. So we've done a lot of stuff so far. We have our end behavior. We have a vertical asymptote in 2 locations. We have 2 x-intercepts, 2 locations. We know that they're crosses. That's great. We know that this doesn't do anything for us. The next thing we're going to do is evaluate for 0. So we plug in x equals 0. You can do it anywhere. You can do it here on your factored version, simplified version. You can do it here. I think honestly it's easiest to do it at the beginning. So if we plug in 0 there, 0 minus 1 over 0 minus 4, we get the same y-intercept that we do in the previous graph. This graph's going to look decidedly different, but it does have the y-intercept of 0, 1/4. Now, again, we don't have a horizontal asymptote at all in this case. Definitely not one that's equal to a constant. We don't have an oblique asymptote. We have just our standard quadratic sort of looking end behavior. What that means is that there's no function to set equal to, or that there's nothing to set our function equal to and solve. We don't have to worry about that step. The next couple examples we will, and I'll show you that. But right now, we say there's no step 5 because there is no horizontal asymptote equal to a non-zero constant. There's no oblique asymptote at all. You don't have to worry about it. It's not going to intersect this x squared end behavior, not to worry. Step number 6 says, let's take everything we just learned. Let's put it on the x-axis as a number line. Let's plug in some additional points, and then we'll get a good graph. So what that means is that in order, we're going to take our x-intercepts and our vertical asymptotes, and we're going to put them here. So x equals -2 and 2. Those are odd vertical asymptotes. We're going to write that down. Our x-intercepts are -1 and 1. We know that those are x-intercepts and they're going to cross. Then what we're going to do, and this is kind of the tedious part, we're going to plug in some values for every interval, and there's 1, 2, 3, 4. There's 5 of them here. So think of the x-axis as a loaf of bread. You just sliced it 1, 2, 3, 4 times. You slice a loaf of bread once, you have 2 pieces. We sliced it 4 times, we have 5 pieces, 5 intervals. We need a point in every one of those. So I'm going to model that right now. So I have some values here. I've got 3 and positive, -3 and +3, -1.5, +1.5. I'm not plugging in anything here because I'm going to show you that the y-intercept can work if you have one. What we get, if we evaluate for -3, we get 16. Now sometimes, using the stuff I've taught you can be helpful, because if you think about it real, oh man, I hope that you're seeing it. Is that even, or is that an odd function? If you think about it, that's even, because all I have is those even exponents. If I evaluate for -x, I get the same thing out, that's even. What that means, think about it. Even means opposite inputs give you the same output. If I evaluate -3 and 3, I'm going to get 16. That just saves me a whole lot of work. I don't have to evaluate for that. That's because we know it's even. Even is symmetric about the y-axis. Opposite inputs equal outputs. If we evaluate for -1.5, we get about 2.3. Negative. And we already know that our y-intercept is 0, 1/4. Now we're actually ready to graph. We're going to go in the same exact order as our steps here. So number 1 thing we're going to do is check this out. This is pretty cool. We can put our end behavior of x squared. Wait a minute, what? Yeah, if we picture this as x squared, so just remember that this is kind of a squished graph because my scale is wrong. So I would have to plug in 2 to get 4. That's a little better. I'm going to put that end behavior up there. I'm going to show you that this is going to work with that end behavior. So we do that first. We get the horizontal asymptote, oblique asymptote, some sort of end behavior. Then we take a look at any vertical asymptote we have. We have 2 of them. We've got one at -2 and one at +2. They're both odd. So we're going to draw those, but we're also going to put that this is odd and odd. So we're going to interact with that asymptote at opposite infinities. One's going to go to positive infinity, the other side's going to go to negative infinity as far as the function's concerned. So we've done that. Now we go ahead and we graph or we plot our x-intercepts. Our x-intercept has to be -1 and 1. They're both crosses. So we don't put a little dotted line. These are not balances. These are crosses. We put our y-intercept of 0, 1, 4. Remember, this is 4, and so this is really, really down there close to the x-axis. Now we're almost ready to graph. Notice something. This might be quite difficult to do if we didn't have any of these other points. So you have to think about this going, what in the world does that look like? Well, it's definitely doable. If you interact with this, your graph would have to have that as a y-intercept. Notice how important that is. If you didn't know that, there'd be multiple ways to go and do this. You can cross end behavior. Don't worry about that. You can't cross vertical asymptotes. And so how this graph would have to look, if these are all the x-intercepts, which they are, and all the asymptotes and end behavior we have, which we have that, then this graph has to go like this. That's a must. It has to cross, hit that, and cross. Only way you can do it is to do this with those vertical asymptotes. So if it's doing this, and we have 2 odd vertical asymptotes, this infinity is opposite of this one. So this would go this way, this graph would do this. It would follow that end behavior, but also have to pay attention to that vertical asymptote. This graph would also do this, due to 2 reasons. Number 1, it's symmetrical. So this part and this part have to look identical. It's symmetric about the y. It's an even function. But also it's got to work with, it's got to mesh with this end behavior and with our points. Now, putting the points on there is going to make it a lot better. So -3, 16. And +3, 16, those are symmetric values. We already knew that. 1.5, -2.3. And likewise, and now this clears up a whole lot for us. So we know that this graph is going to firstly do this. Take care of the intervals that have the physical points in there, and x-intercepts, a lot of them. That's oftentimes easier to do. So we know that this has to follow those values. Now there's no question, because this goes to negative infinity and we have an odd vertical asymptote, we have to have opposite infinities. We also have to follow that end behavior. Here's the things we don't know about it. That's a fairly decent graph. Here's the things we don't know. We don't actually know where our local minima are here. They don't have to be at that value. They could be, but they don't have to be. We need some calculus to figure that out. So that's why this is still, we are still sketching. It's getting closer to a graph by the techniques I'm showing you, but that's about it. So hopefully this is making sense. Like the order works. These steps work. Just do your end behavior first, then your vertical asymptotes, then your x-intercepts, y-intercept, make your number line, do some additional points that will really help you, and then everything has to work together. If you find out that, man, one of your points is off and you cannot make your odd vertical asymptote work where your point is now up here or something, well, then you've messed something up. And so that's a time to check your work. Like, I screwed it up. And it'll happen. It'll be okay. But hopefully these steps are making sense to you. You're able to follow it. You're able to see like what we've done in the past now come to fruition. Like, oh yeah, hey, all this stuff we've done in little chunks, now we're putting it together. I'll see you in a minute for another example. Okay, let's work our way through another example. So we have this next one, definitely a rational function. We're going to see in this example, now I'm going to slow down for a little bit, when you have a horizontal asymptote that is not 0, you have to set your function equal to it and see if we intersect. I'm going to show you how to do that. So number one, when we have a rational function, the first thing we want to do, take our leading terms, put them in a ratio, simplify, and find our end behavior. Sometimes it's going to be a horizontal asymptote. So we take our function, and we say this is about equal to, as far as our end behavior goes, going to be modeled by our leading term of 3x squared over x squared. Now keep in mind what we're doing. Our leading terms give end behavior, so when putting them in the ratio, we're finding out the end behavior of our rational function. And if we simplify, we just get 3. We go, well, so what's that mean? Well, that means that as x approaches positive and negative infinity, 3 is a constant. 3 does not change. 3 means, oh yeah, my function will get closer and closer to 3 as we continue on. This is what end behavior does. End behavior says as x gets really, really big, our function kind of gets closer to this value. So this takes over. The leading terms take over. And so this says we have a horizontal asymptote at y equals 3, a constant of y equals 3 at which our function will get closer and closer and closer as x gets bigger and bigger and bigger. That's what that means. Now, formulaically, you could do, oh yeah, when my exponents are the same, you just get the coefficients of leading terms and it's 3. That's true, but I want you to understand why. The why is that as you simplify your leading terms, which have your end behavior, you get a constant out of them. That means that the function, the numerator and denominator, with really, really big numbers, are going to get closer and closer to that ratio, 3 over 1, 3 over 1, 3 over 1. It's getting closer and closer to that. It's getting closer to this value of y equals 3. That's why we have a horizontal asymptote at y equals 3. So right now in my head, I'm thinking, oh, that's a horizontal asymptote. That's not 0. I'm going to have a step 5. In this step, I'm going to be setting my function equal to 3 and solving it. We're going to find an intersection there. We'll slow down for that in just a little bit. On step 2, factor everything as much as you can, because this is where we're going to look for a whole or a vertical asymptote. So on our numerator, we can factor out a GCF of 3x. On our denominator, we have that sort of a diamond problem or a quadratic that we can factor. Honestly, you could do quadratic formula here if it's not factorable by something easy, but that would lead to some seriously awkward vertical asymptotes. It can happen, but probably not. So don't go quadratic formula right away. Try to factor. In this case, we have x plus 4 and x minus 3. Now, since we're looking for a vertical asymptote or a whole, we first check out our denominator. We say, hey, these two factors here, if they equal 0, that's a problem for us. So we identify that they're a problem, that we know that at x equals -4 and at x equals 3, we're going to have some issues. Either we're going to have a whole or a vertical asymptote. Now we look at the factors and say x plus 4, from where we got this discontinuity, this does not cancel. Therefore, that x equals -4 is going to be a vertical asymptote. If it cancels, it's a whole. If it doesn't, it's a vertical asymptote. Furthermore, because it has a power 1, it's odd. Here we have also, this 3 came from a factor x minus 3. It does not cancel, therefore it's a vertical asymptote. And it has an odd exponent, therefore it's odd. Now we're on a roll. Next up is our X-Intercepts. So once you have it factored, it's really nice. We take our numerator, we set it equal to 0, and we solve it. The numerator is the only place where a function can actually equal 0. The denominator equaling 0 gives us discontinuities. Those are vertical asymptotes in this case. So when our numerator is equal to 0, I told you to put some parentheses around any factor that has a variable in it. And what that does, that says our real factor here doesn't involve the 3. The 3 is telling us that this is going to have a horizontal asymptote of 3. Also says it's kind of a vertical stretch. But that x equaling 0, when you do it this way, shows you have a multiplicity of 1. Oops. Had that one in my mind. Having x equal to 0 with that parentheses and that exponent says you have a multiplicity of 1. That's going to be a cross. Same thing here. X minus 1 equals 0. X equals 1. And because this comes from a factor that has a exponent of 1, you have a cross. Odd multiplicity gives you crossies. Now for our y-intercept. So when we take our y-intercept, we just plug in 0. Pretty much it's easiest to do that here. You certainly can do it here in your factored or simplified version. It doesn't really matter. So we're going to evaluate x equals 0. Here we get 0 over 0 minus 0. That's 0 over negative 12. Well, 0 over negative 12 is 0. Remember, 0 on the numerator and a constant on the denominator is going to give you 0. So we have found a horizontal asymptote of 3. We've found our vertical asymptotes. Our x-intercepts are pretty easy once you have it factored. Our y-intercept, we just evaluate for x equals 0. We got it. Now step number 5. If you have a horizontal asymptote that's not 0, if you have an oblique asymptote at all, you have to set your function equal to that and solve it. And the reason is, it's because a horizontal asymptote takes over as x approaches really big numbers, positive and negative big numbers. Things can happen in the middle. In fact, our function can cross that horizontal asymptote, and it does here. I'm going to show you that. So when we have a horizontal asymptote that's not 0, again, why not 0? Well, if you have a horizontal asymptote that equals 0, that's just the x-axis, and you've already found x-intercepts. So setting your function equal to the horizontal asymptote of 0 is just redoing work. It's just redoing finding x-intercepts. It's got to make sense. If we don't have a 0, we're going to find some additional intercepts of, but not of 0, of y equals 3 in this case. So take your function, set it equal to this if it's not 0. When we do that, a lot of things should cancel out. We typically, if we don't get an intersection, we get something nonsensical, like 0 equals negative 2. If we do get an intersection, we're going to get x equals some value. And you're going to see that right here. How we deal with equations when we have fractions, multiply your denominator, both sides. You would have already simplified this. And in fact, you could do it here. It doesn't really matter where you do it. Multiply both sides. I like to do it from the original or the simplified version. If you've canceled factors, that's easiest. Here we didn't do that. So we're going to multiply both sides by x squared plus x minus 12. So both sides get multiplied, no problem. If we distribute, you're going to see it right away. You're going to see that a lot of things are going to cancel out. Like these x squareds, we have some, these do not. But if I subtract 3x squared, those would cancel. If I add 3x and add 36, we get, notice I'm adding 3x to both sides, that's 6x. I'm adding 36, that's 36. If I divide by 6, we get 6. We get x equals 6. That right there, when you still have an x, and it says x equals some constant, you are getting an intersection. You're going to have to find that somewhere. So we're going to take that 6, plug it in, and find the point of that intersection. Now, what I said is if you still have an x. Well, what's that mean? If you don't have an x, if all of your x terms cancel, That is what tells you that your graph is not intersecting your horizontal asymptote. That's what says it. So solve it. If you still have an x, yep, you have an intersection. You're going to have to right now find where that point is. So we're going to evaluate 6 comma whatever in our function. If it comes down to here and you get like something like -2 equals 0, and you go, all my x's disappeared. You go, yep, it sure did. That means that your graph does not cross this. That's a nonsense statement. It says there's no solution to that. It's no solution means that your graph does not cross, this graph doesn't cross that graph. That graph is a horizontal line. That's your horizontal asymptote. If you come up with this, it means these don't intersect. If you come with an x that says they do intersect, find out where. Now, the where should not be hard. Plug in this 6. Plug it in where? Well, you could plug it in here. You know what you're going to get? You're going to get the same thing as if you plugged it in here. Wait a minute. Really? Yeah. Because you just set these functions equal, didn't you? So you said they're equal. So if I plug in 6 here and I plug in 6 here, it's going to give me the same value. It's going to give me out 3. Notice what you're doing. You're trying to figure out where your graph crosses this horizontal line, right? The horizontal line is always at 3. So if you figure out, oh, I'm going to cross it at x equals 6, but it's got to be at 3 because that's a horizontal line. So this is going to be 3. And if you want to take the time, if you don't believe me, plug in 6 here. I really don't want to do it. You know what I'd do? I'd plug in 6 like here. So if I did 6 minus 1 is 5, 5 times 6 is 30, 30 times 3 is 90. 6 minus 3 is 3, 6 plus 4 is 10, that would be 30. 90 divided by 30 is 3. But that was much harder to do than just saying, it's 3. Yay. That right there is where we're going to intersect our horizontal asymptote at 6, 3. Next, what we do is we put all of our important values on here. So we're going to have a few x-intercepts, a few vertical asymptotes. We're going to put some more points on there too. So I know that at -4 and 3, we have odd vertical asymptote. I know that x equals 1 and x equals 0, we have crosses. Those are x-intercepts. And now we're going to have to plug in some other values. You might be able to get away with this as the point in this interval. No problem. You could do that. Probably be better to put something else on there, but that's kind of up to you. I would definitely recommend plugging in some points on these other intervals. So I'd plug in -5. I'd plug in -1. You have to plug in something here because you don't have a y-intercept that's not already listed. So I'm going to plug in 1/2. Plug in 2. I'd probably plug in 4. Okay, and here's the values that I got. I got a negative as 11 and a quarter, 11.25. We got a -1/2, 1/15, -1, and 4.5. Keep in mind we also have that point, so that's going to help us out a little bit too. And now we're ready to graph it. Man, it's a lot of work. So we're going to take our horizontal asymptote first at y equals 3. We're going to put that up there. Next we're going to do is we're going to take our vertical asymptotes. We're going to put them on the board. We're going to say odd. A horizontal asymptote doesn't have odd or even. You have to have some other points to figure out how you're going to interact with that. You can do it with some calculus, but we don't have that right now. I should say you can do it with some limits, but we don't have that right now. We do have that those are odd. We also have that we have some x-intercepts, one at 0, and one at 1, and they're both crosses. And that's kind of awkward. They're really close together. So we're going to have to know right now whether we're doing this or this. We also have to know that so that we interact with our horizontal and vertical asymptotes appropriately. Thank goodness we put in some extra points here, and thank goodness we have that. That's a big one, because that would tell us a lot about this graph. So if I did 6, 3 right now, notice if I find out where my graph crosses the horizontal asymptote, it better be on the horizontal asymptote, right? Because that's where it intersects. It's what we did. Intersections happen where you set functions equal. We set functions equal to find out where they cross. Okay, what crosses here? If we set it equal to the horizontal asymptote, it better be crossing on the horizontal asymptote if it does. So that helps us a lot. Now we're going to put some of these other points. So -5, positive 11 1/4. -5 and 11 1/4. We also have -1, -1/2. We've got 1/2, 1/15. That's right above the x-axis. But it's a huge point, isn't it? Because we know now that we have to have no x-intercepts here. Come up, hit this point, cross, hit it, cross, and go back down. That must happen. At 2, we have -1. That verifies that for us. At 4, we have 4 1/2. And this is going to give us a fairly clear picture of what's going on. So we know, and I'm going to do this from the place where I have the most points. And the most points is typically around the y-axis. Doesn't have to be there, but it typically is. So we have our x-intercepts within our vertical asymptotes. We have this, not y-intercept, but another point above the x-axis. So we know that we've got to do this and this. It might be helpful to have a couple other points in here. We also know, because our vertical asymptotes are both odd means opposite infinities. We have to do this, hit this point. We also, at that point, I'm going to talk about that in a minute. We do opposite infinities and somehow hit our horizontal asymptote, or well, come close to it on that side as well. Now, what about that point? This is where it gets a little weird. So we cross this horizontal asymptote, but it's still there. We also have an odd vertical asymptote. This is true. You had that point. You have this opposite. You have to be coming from up here. It's got to be decreasing. It's got to go through this point. It also has to touch this point. So what in the world happens? Here's what happens, and we would know this with some Calc 1 doing a local minimum. We would know that this hits this point, goes down, and then eventually comes back up and hits that, gets close to that horizontal asymptote. It does a little kind of dip here and gets closer and closer as we get to infinity. So there's a little dip, but it crosses it and comes back up and gets really, really close to that horizontal asymptote. So we wouldn't know that if we hadn't checked for this. We probably would have made the mistake of just coming down here and floating above it, and that's not what happens. It hits it and it comes back to it. So that's why I wanted to show you this example, because some fascinating or sort of interesting things happen with the horizontal asymptotes if we intersect them. So I hope that makes sense. I hope that this is kind of gelling together for you, the sequence of steps. I consider this to be a fairly difficult problem to do. So if you're handling it, great job. You're doing well. I'll see you in a minute for another example. Okay, I hope you're ready for another one. This one's got a hole in it. We're going to see exactly what to do with a hole. That a hole is not something on the x-axis. A hole is something that's off of the x-axis, typically, that we need to see where it's at. So we're going to do that and show you exactly what to do. So step number 1, we got to find some end behavior. We take our leading terms, we're going to put them in ratio, simplify, and understand what that does. So leading terms here. Leading terms say that if we simplify, we get 2. That's a constant. Think about it. If your function is taken over by your leading terms, you put them in ratio and you get 2, that means as x approaches positive and negative infinity, this function gets closer and closer to 2. That says that you have a horizontal asymptote at y = 2. This is our end behavior. This is exactly what our function is going to get closer to as we get really, really big and really, really negative. The next thing that we do is we factor everything. So we're going to take a moment and factor our function, both numerator and denominator. So if we do I taught this technique a long time ago, but if we do this and divide by our a, then what we're going to get is two factors. We get this x minus 2 and 2x minus 1. On the numerator, we got a difference of squares. I think we've seen it 3 times already. I can't stress how important this is when you're finding a whole. Do not cross out your factors until you identify what your domain problems are, until you identify what your discontinuities are. You have to do that first. Because if you cross them out and go, oh, there's a dot, you miss the whole. You're missing a point here, and you can't miss the point about the missing point. You need to find a whole. And so when we factor this, the number one thing we do is we take our denominator, we set it equal to 0, and we say there are 2 factors. Right now there's 2 factors that are causing a discontinuity, a domain issue. One of them is x minus 2. The other is x plus 2. So we identify what they are after we identify that they are. So these are domain problems. Now we identify what they are. So we look back at this and we say, okay, at x equals 2, I am going to have a serious issue. At x equals negative 2, I'm going to have a serious issue. X equals 2 came from x minus 2. Now you look back here and go, oh, x minus 2 is something that can cancel. Now you do cancel it. It is gone, but it's also identified what this is. So when we cancel, we say, hey, at x equals 2, we have a whole. Before you go any further, identify where that hole occurs. So we already know that it's at x equals 2, but that does not mean that you go here and you put a circle around that and go, oh, there's no point on the x-axis at 2. That is not what this means. There's going to be a hole in our function. It's going to be right in the middle of our graph. It's going to look like this. There's going to be a hole. It's going to continue. So what we do is we say, all right, we know right now that we set these equal to 0. We find some discontinuities, some problems. Identify what they are. Oh, I crossed this factor from where I got the 2. I crossed that out. That means that's a hole. Now, figure out where the hole is. How you do that? You take the 2. I know it's not there. We're figuring out where we have a missing point. Take the 2 and plug it in. It will allow you to, now that you've canceled this out. So our simplified function looks like this. I want you to make kind of 2 mental notes about this. The first thing is that this will allow you to find the hole. Plug in your 2, it'll allow you to find the hole. The second thing, everything that you could do with this function, you can now do with this one. So if you want to find x-intercepts, forget that. Use that one. If you want to find out your y-intercept, you don't even have to do that. You can use this one. You want to find a horizontal asymptote, you actually could have used this too. Look at this. Here's 2x squared over 2x of x squared, here's 2x over x. It still gives you 2. It's going to behave exactly the same as that. Why? Because there's only one difference between this graph and this graph. This graph has a missing hole. That's why we have to use this to find it and identify the hole. Let's say that one more time. That's got a missing hole, this one doesn't. But this one came from that. So we know this has a hole at that value. That's why you identify your hole first before you start canceling your junk out. So we've done that. Now plug the 2 in. So 2 would say 2 times 2 is 4. 4 minus 1 is 3 over 4. That's at 3/4. So we are going to put an open circle at that point. And that's going to signify the graph's got to go through there, right? It has to. It's got to go up to it and then past it, but that's going to be a missing hole. That's going to be an open circle for us. Then we identify, okay, at this x equals negative 2 that came from x plus 2 cannot be canceled. Therefore, it's a vertical asymptote and it is an odd. Once we've done that, we find our x-intercepts. X-intercepts are always from numerators. You can set this numerator equal to 0, but I would encourage you to set it equal to 0 after you've factored and canceled. It's much easier. So your numerator is 2x minus 1. If we add 1 and divide by 2, we get 1/2. Now notice, this did come from a factor that has a power 1. It's basically a linear, right? So you can't even have a power 2 in there. This is a cross. Step number 4, we're going to find our y-intercept. We're going to evaluate for x equals 0. You can use this if you want to. It's not all that bad. You're going to get 2 over negative 4. That's negative 1/2. Or you can use this, plug in 0. You get negative 1 over 2. That's negative 1/2. Either way, we evaluate 0. And we got negative 1/2 as our y-intercept. Now step 5. Step 5 says if you have a horizontal asymptote that's not 0, or you have an oblique asymptote at all, you need to set your function equal to your horizontal asymptote that's not 0 and solve it. And if you have an intersection, you have to show that. I'm going to show you what it looks like when you don't have an intersection. You're going to come up with some untrue math statement that goes, what's that mean? It means it doesn't cross. And so I'm going to show you that right now. So we take our function. Now which function? Do you want to take this function or this function? It doesn't matter. So pick the easier one. Take your simplified function, set it equal to 2. Two being our non-zero horizontal asymptote. If we multiply both sides by our denominator, we get 2x minus 1 equals 2 times x plus 2. We get 2x minus 1 equals 2x plus 4. And we subtract our 2x. You go, well, wait a minute, something's wrong. We just canceled out all of our x's and we get negative 1 equals 4. Yes, precisely. Can this actually happen? Can negative 1 equal 4 ever? Well, no, that doesn't make any sense. So what that means is that if this can't happen, then this can't happen. If this is untrue, then this is untrue. This means it's not possible. That means it's not possible for my function to intersect my horizontal asymptote. That's what that's saying. This says there's no intersection here. This says this can't happen, so therefore that can't happen. There's no solution to it. So that says that this graph doesn't cross that horizontal asymptote. There's no intersection. And now we're ready to put everything on our x-axis to model our graph and then graph it. So we have a hole, we have a vertical asymptote, we have one x-intercept. So we're going to put that up there. So we know that negative 2, vertical asymptote, odd. We know that we have an x-intercept at 1/2. That's a cross. We know that we have a hole. And that's a hole. Now we're going to plug in some extra values. We're going to evaluate for every one of these intervals to make sure that we have an accurate graph. You can use your y-intercept for this one. That's totally fine. So I'm going to do 1, 2, 3 since we already have something in there. So I'll evaluate negative 3. Use 0 here. You'll use 1 and 3. So this is going to give us 7. 1/3 and 1. And we are ready to graph. The first thing we're going to do is we're going to put our horizontal asymptote on our graph. After that, it's time for our one vertical asymptote at x equals negative 2. And we know that's an odd vertical asymptote. And now for our points. So we have our y-intercept. We know that our y-intercept is 0, negative 1/2. That's right down there. We know that we have an x-intercept at 1/2, that's a cross. That's right there. Then we go ahead and we say we have a couple other features that we need to notice. We have a hole. Your hole is not here. Notice that would create some sort of really awkward thing here. We have to match up with this. So it would be impossible for us to cross, cross, and then not cross again and hit a horizontal asymptote. There's no other x-intercept beside the one that we have, so we cannot cross the x-axis anywhere else. We also know that we do not cross our horizontal asymptote. That's what this said. You do not cross it. So there's no coming up here, there's no coming up here, going back down. There's simply, you have to do this. And that is what this does for you, right where we have our hole. This 2, 3/4 says at 2, 3/4, we have an open circle. Our graph is going to go to that circle and go past that circle. Now we fill this out with some other values. We know at -3 we got 7. We know at 0 we had -1/2. We already used our y-intercept. At 1 we have 1/3. And at 3 we have 1. This is going to be really clear if you do it this way. I hope you're seeing how these extra points really clear things up. So we know for sure, like there's no other x-intercept, so we know for sure we've got to do this. And then we have to go through that point. We have odd. Odd means opposite infinities for vertical asymptotes. We do not cross a horizontal asymptote. That's what this said, no intersection. So you don't cross it, you go right to it. You don't cross it, you go right to it. The previous example, we crossed it and had to come back to it. That's not happening here. That's how we do our holes. What we do is we find them, we figure out where they're at, and we put an open circle there. It's very useful because it gives us another feature of our graph. The last thing I'm going to say is that this graph is the same as this with that filled in. That's what it would look like. This graph has just that missing hole. It should be interesting. It's kind of fascinating that they're so close. This one is missing that hole, which is why we had to do it this way. Figure out your hole first, then cancel it out. Hope that makes sense. We're down to one more kind of serious one, and then some special cases and things I want you to know outside of just taking a function and graph it, maybe how to go backwards, things like that. Okay, we're hammering along. This is going to be the most kind of labor-intensive one. So this has an oblique asymptote in it. I got to show you how to find it. I got to show you how to find where your function intersects it and what that means for our graph. So it'll take a little bit of time to explain that. But it's going to be the same process that we've gone through. So the first thing we do, find your end behavior. Now your end behavior can be one of 3 things. It can be like a power function, odd or even, positive, negative. It can be a horizontal asymptote at 0 or a constant, or it can be an oblique asymptote. You are going to find an oblique asymptote if this power is greater than that power. Why? Because if you do your end behavior, and you take your leading terms and you simplify them, you're going to get x to the first power. X to the first power is a linear function. Remember the second example. We had x squared. That was a parabola. X to the first is a line. It's called a slant asymptote or an oblique asymptote. That's what that is. However, unlike with your x squared, what we have to do is we have to figure out where this thing is exactly for a slant asymptote. So what we're going to have to do is our long division of polynomials, and that can be a little tedious. So when you find out that you have an oblique asymptote, go one more step. Take your numerator, divide by your denominator, and do exactly 2 iterations of long division. And here's what I mean by exactly 2 iterations. Just divide your first term by your first term. So x cubed divided by x squared is x. Multiply. So x cubed minus 9x. Subtract, and we go, right? X cubed minus x cubed is 0. 0x squared minus nothing is still that. 0x squared, and we have 0x minus -9. That's plus 9. That would be 9x. And then check one more. Does this divide this? No, it doesn't. If you had an x squared here, yes, you would. So let's say that was like x squared. X squared divided by x squared would give you 1, and you put plus 1. This right here, your quotient, is what your oblique asymptote is. This is the function for it. So y equals x. This does not matter. So I'm going to show it to you right now. If this were the case, like let's pretend that this were like a 2x squared or something. Well, then when you subtracted x cubed minus x cubed is 0, 2x squared minus nothing would be 2x squared, and this would be plus 9. We would do one more iteration. You'd say 2x squared divided by x squared would be 2, and then you'd have x plus 2 as your slant asymptote. You'd go to 2, go up 1 over 1, and draw a dotted line that goes diagonally. That's what would have happened. Now, we didn't. We didn't have anything right here. So as soon as you get to x plus something, or x minus something, or 2x, whatever, as soon as you get a linear equation, you're done. We didn't have this, and we didn't have that. So this was completely empty. That was just 0x squared. Which is why we just get x and not x plus anything. So our oblique asymptote is y equals x. And now we go and factor everything to figure out where our whole or vertical asymptote, if we have any, are. Now, if you don't remember how to factor x cubed minus 1, that would be a difference of cubes. How you factor difference of cubes, you take the first thing being cubed, you put it here, but you square the second one. The last thing being cubed is 1, we put it here, but we square the second one. Multiply the 1 times your first factor, that would be 1x. Put the same sign as you start with, that's minus 1, opposite sign, and always a plus. So this is going to factor as x minus 1 times x squared plus x plus 1. If you don't remember that, you might want to go check out like intermediate algebra when we factor difference of cubes. So that's on there, you can check out that video. On the denominator, we have a difference of squares again. That's going to be x minus 3 and x plus 3. One nice thing about the difference of cubes and sum of cubes is that this is not factorable. So it's going to be an irreducible quadratic, which is great because that means we only have one x-intercept here. Now, as far as our vertical asymptote or whole, what we do is we identify that we have problems. So we know that we're going to have problems on these two factors. We write them down first. And we solve them. And then we identify them. So x equals 3, that's a domain problem. The discontinuity comes from this factor. This factor has a power 1. This factor is not cancelable. It's an odd vertical asymptote. Same thing here. Since we've already factored our function, we set our numerator equal to 0 for our x-intercepts. The only one that actually is able to equal 0 are the linears that you factored, non-reducible quadratic or irreducible quadratics, like this one that you can't factor. Try quadratic formula if you want. We're going to get 1 minus 4, 1 squared is 1, minus 4 times 1 times 1, that's negative 3 instead of the square root. That is an imaginary number. This is not going to give you any more x-intercepts, just this one. So x minus 1 equals 0. That comes from a factor that has a power 1. This is going to be a cross. For our y-intercept, we just plug in 0. It's honestly easiest to do it here. So in your original or your simplified function, if you had holes. So from here, we plug in 0. We're going to get positive 1/9. Now for a bit of awkwardness. If we have an oblique asymptote or a horizontal asymptote that's not 0, you gotta set your function equal to it. I would recommend setting your original function or your simplified if you cross out some factors. That's great. But here we have to set this equal to whatever we get here if it's not 0. So we take our function. The reason why we're not using this one is it's already factored. We have to distribute it. That would be a real pain. The only time you use something from here for this step is if you have canceled out a factor. and it's something that's nice, not factored version anymore. Otherwise, we go right back up to here and we say, if we had a horizontal asymptote that's not 0, if we have any sort of oblique asymptote, set your function equal to that. So we're going to set it equal to x. If we multiply, and we distribute, and we simplify a little bit. So if we subtract x cubed, both sides, these are going to cancel. We're going to get -1 equals -9x. Hey, look, you haven't simplified all your x's. That means this function will intersect this y equals x oblique or slant asymptote. It will happen. Where it happens is if you divide by -9, x equals +1/9. 1 divided by 9, or -1 divided by -9 is -1/9. But remember, we've just found an intersection, right? So we're not going to go to 1/9 here and put a little point. What we found out is that this function crosses this function at that x value. You need a point when you're crossing a horizontal asymptote and when you're crossing an oblique asymptote. So we're going to cross at 1/9, comma, something. How do you find the something? Well, there's two ways. And we saw this when we intersected that horizontal asymptote. You can take 1/9 and you can run it back through your function, or you can run it back through the function you're crossing. This is way easier. So if I plug in 1/9 here, I'm going to get 1/27 minus 1. I'm going to get, oh shoot, no I'm not. I'm going to get way more than that. 1/729 minus 1. I'm going to get 1/81 minus 9. I'd divide those things. You know what I get? I get 1/9. Why? Because here's the other function. The other function is y equals x. What's your y value when x is 1/9? That's what we're doing. We're figuring out where this function crosses this. So all we have to do is plug it into whichever one we want, whichever one's easier. You see, if we're finding out where these intersect, they have to have the same x value and same y value. We found out these intersect when your x value is 1/9. So you have to plug it in to figure out your y value. Plug it in here, you're going to get 1/9. Plug it in here, you're going to get 1/9. Which one's easier? That one. So if I plug in 1/9 to my x value of the function I'm crossing, my oblique asymptote, it's going to also give me out 1/9. That's a little awkward, but that is a point on the graph. That's 1/9, comma 1/9. Now, why is it the same input and output? I hope that makes sense, because that's exactly what this says to you. This says that for y equals x, that diagonal line, your output equals your input. So if I have an input of 1/9, I have to have an output of 1/9. That's got to make sense. The next thing we do is we take all of our important values and put them on here on our x-axis. So we have a few points. We have a couple vertical asymptotes that are odd. We have one cross at x equals 1. I'm not going to put that point on there, but I am going to recognize that this is a point on my graph. I'm going to have to put that there. It'll be on my oblique asymptote. I'm also going to plug in a few other values. So I'm going to plug in something like -4. I'm not going to plug in 0 because I already have that. I have my y-intercept. I'm going to plug in 2. So I'm going to take these values, I'm going to plug it into my function. I'm going to use this one because it's a little bit easier to evaluate for me right now. Okay, so I've taken the time to evaluate. I plugged in -4, got -9.3, 2, got -1.4, 4, and got 9. We're ready to plot this along with our intersection between our function and our oblique asymptote and our y-intercept. So we start the same way that we went through this. First thing we're going to do is show our end behavior somehow. So I'm going to show my oblique asymptote. Keep in mind, it's not perfect 45 degrees because my scale is a little bit off. I've kind of compressed this a bit to allow for our space. Next thing we do, we put in the vertical asymptotes that we have on the graph. And we know that they're both odd. Finally, we put our points on there. We put our x-intercept at 1. We put our y-intercept at 1/9. We put our intersection of our function and our oblique asymptote. So this has to be on this dotted line, this diagonal line. That is our intersection. And this is a little weird. So there's a 1/9 for your y-intercept and a 1/9, 1/9 for your intersection between your graph and your oblique asymptote. This is one reason I put this on here, is because this is going to show you that this technique of graphing or sketching doesn't give you everything that you probably should have on a real graph, and we'll talk about that when we get there. But we put it on there. We have our 0, 1/9, that's this one. We have our 1/9, 1/9, that's that one. We have our x-intercept of 1. We know it's a cross. We know it's not a bounce. And then we put our points on here. So -4, -9.3. We also have our y-intercept already. We do 2, -1.4. And we have our 4, 9. All right, and using what we know about this, what we know is that we found trusted, we found all the x-intercepts. We also know that this is odd, that is odd. We also know there's an oblique asymptote that our function has to follow. We also know that if we found all the x-intercepts, we cannot come back and cross this anywhere. That means that because of that y-intercept, we probably should have something. Yeah, honestly, we really should have had something in here as well. We don't, it's fine, but we probably should have a point in here. And that would show it a little bit more clearly if we plugged in -1 or -2, that this has to behave this way. That would be an appropriate step to take. Now, how in the world does this happen? What happens there? What probably happens is there's a little dip. So a little rise. So this probably rises and goes back down. It's not flat. Don't do flat. It probably does this. A little rise in there, but that teeny local minimum or local maximum, depending on what it does, that would be found with calculus. So we'd have to find that. Here we know that it's got to follow this. There's no x-intercepts. Has to hit our y-intercept. Has to hit this intersection between y equals x. Has to hit our x-intercept cross. Has to hit this point. Has to be -infinity. Can't come back up. Because this is odd, we have opposite infinities. We also know that we do not intersect the y equals x line, that oblique asymptote, anywhere but here. Otherwise, it would have shown up when we set them equal. So we can trust that this doesn't intersect. This just loops around and follows that oblique asymptote. Because this is odd, our infinities have to be opposite. And something quite similar happens here, that we follow that oblique asymptote. That's about as good as I can do with hand sketching and this information. Is to get a look about like that. That's why we still call it a sketch. It's closer to graphing. We have it much more accurate than if we didn't have these points, but it gives you a fairly clear picture of what's going on with your graph. So we have just a couple more examples. One that's very quick graphing, and then some special cases, things that we can do. Okay, this is going to be a fairly quick example, Leonard version of quick, of something that's already factored for you that you really don't want to distribute, and how to deal with that. Also how to deal with a bouncing x-intercept, how to deal with an even multiplicity vertical asymptote. So that we're gonna explore those things as we go through this. So we take a look at it, we go, all right, x squared, x minus 1 squared over x plus 3 to the 4th. Should I distribute all that? No. No, when you're dealt this and you still need to find end behavior, even like a horizontal asymptote, do it the way that I showed you with the sort of fake distribution. And what that's going to do is that's going to say, take your largest powers that you would get if you were to distribute. And so we'd say, here's an x squared, here's an x to the 2nd power, that's x to the 4th on the numerator. And if you were to distribute this, you'd get an x to the 4th. Well, that's 1. X to the 4th divided by x to the 4th is 1. This is a horizontal asymptote at x equals 1. I'm sorry, I misspoke. At y equals 1. We have a horizontal asymptote at y equals 1. So as x approaches positive negative infinity, this graph is getting closer and closer to 1 somehow. The next thing we're going to do is we're going to factor everything. Hey, look at that. It's already factored. That's fantastic. So it means if you were to distribute this, you'd have to refactor it. Don't do that. just take what they're giving and say, hey, we're going to have a problem if this factor, x plus 3 equals 0. That would be a discontinuity. So we say that we have a problem, we show what the problem is, and then we identify the problem. So x minus 3 comes from x plus 3. This factor does not cancel. So right here, this says that this is a vertical asymptote, and it has an even multiplicity. Then we find our x-intercepts. So with an x-intercept, we take our numerator and set that equal to 0 from our factored version. Now, what I told you is that we're really concerned with the factor equaling 0 and then the power of the factor telling us whether we cross or bounce. So our factors here are actually x and x minus 1. I don't want you to think of x squared as the factor. I want you to think of x as the factor and the power 2 as the multiplicity. So x equals 0 by the 0 product property, x minus 1 equals 0 by the same property, x equals 1, no problem. But this is a factor x. It's got a power 2. That means that we have a bounce or a touch. This also has a power 2. This is another bounce or a touch. Now we find our y-intercept, but if we do that, hopefully we understand that if we evaluate 0 and we have an x-intercept of 0, 0 for x-intercept is going to be 0 for y-intercept also. And you can try it if you want to, but plug in 0 here, you get 0 times, I really don't care. 0 times anything else is 0 divided by something that's not 0. Otherwise, we would have had a hole because something would have canceled. It's going to give you 0. Now, you'll notice that even though we have a horizontal asymptote of y equals 1, I'm not setting my function equal to that 1. And the reason is, if I do that here, I'm going to spend a very long time distributing. So x plus 3 to the 4th power is x plus 3 times x plus 3 times x plus 3 times x plus 3. I use binomial expansion. Either way, it's going to be kind of nasty. So we're not going to do it. If you have to, then you have to distribute that. And if you figure out where you have an intersection, if you do have one. I'm showing you a quick sketch to get a picture of this graph without doing a whole lot of work. So this was quick, this was quick, this was quick. Now let's see that this gives a pretty decent graph without having to do everything about it, without plugging in points even. So we can get a nice sketch. So we're going to firstly do our horizontal asymptote at 1, our vertical asymptote at -3, and put that it's even. That's different. We've never seen that before. Then we put our x-intercepts. We know that we have 0 and we have 1. But we also know that those are bounces. So I showed you a little kind of trick here. If you put a little dotted line in the neighborhood of those x-intercepts, that says that we're going to bounce. Now, if those are the only way that we intersect with our x-axis, we probably need at least one other point to say where we're even at. And so I would do something like plug in -1. -1 would be good, because if we know that we're down here, we bounce, well, that doesn't make a whole lot of sense because we have to intersect that. So let's figure out where that -1 is. So we're going to evaluate f of -1. Okay, I've taken the time to evaluate two values. I've plugged in -1, got out 1/4, plugged in -2, and get out 36. And the reason why I did both is because I don't want to take the time to see if this function intersects this horizontal asymptote. Here's the reason why I plugged in 2 points. If I plug in -1 and get out 1/4, and plug in -2 and get out 36, that's way up there. That means that this value, let's put it here, even though it's way higher than that, that means that this is going to have to cross that horizontal asymptote. So in plugging these 2 points, I eliminate setting this equal to that and trying to solve it. So that's, now I don't know whether it crosses here and comes back down, but I don't think it does. So here's what's going to happen with us. What's going to happen is that we know that in order to hit this point, we're going to have to, and we know that in order to hit this point, we got to come from way up here. We're going to have to cross, hit this point. We're going to have to bounce. We're going to have to bounce again. and interact with that horizontal asymptote. Now, what I admit to you is that I don't know if this actually crosses and comes back down. I'm not sure. We'd have to set this equal or use some calculus to figure out whether that happens. What I do know is that there's a bounce here and here, so there's got to be some sort of turning point in there somewhere. I also know that because this is even, I have these equal infinities. I also don't know whether this is crossing here and coming back up. We need a little bit more math to do it. All I really wanted to show you in this example was how to deal with an even. Even has even multiplicity, and therefore for vertical asymptotes, the same infinities. Also, when we have bounces, just keep in mind we're not crossing there. So this graph looks about like this. So we're going to have to come down, bounce, bounce, and come back up. So I hope that makes sense to you. We'll come back with a couple special cases and then we'll be done. Okay, last little bit, some special cases, an awkward formation of a function and going backwards from a graph into a function, which is not as hard as it seems. As long as you follow what I've shown you, you'll be fine. So what to do on something like that? Number one, I want you to understand a couple things about this. There are some other ways to do it. You can look at this and get some important features out of it, such as you can still get a vertical asymptote at 0. You can actually get an oblique asymptote at 2x. So that's sort of valuable. What might be hard to see is that you don't have any x-intercepts. That can be difficult. So my advice to you is take this, find a common denominator, and make one fraction out of it. It'll make it in the form of a rational that you're used to. So because our common denominator would be x, we'd multiply the first function by x over x. And we get this function (2x squared plus 9 over x). I'm not going to spend a whole long time on this. This is a lot easier to see, that you have a vertical asymptote at 0. It's also hopefully easy to see that if you set your numerator equal to 0, there is no way that you can make that happen. 2x squared plus some other number in no way ever equals 0 without imaginary numbers. So you can't do it. There are no x-intercepts. There's a vertical asymptote at 0. And there's also an oblique asymptote. We can see that 2x squared over x gives us 2x. In fact, that plus 9 without an x being up here, if you were to do long division of polynomials, you would get 2x, you'd multiply, you get 2x squared, subtract, you get 0, bring down 0x, and you go, oh, it doesn't go in. Hey, there's my oblique asymptote. So how this graph looks, I'm just going to give you a really quick picture of it. This has an oblique asymptote at y equals 2x. This also has a vertical asymptote at x equals 0. And we know that it's odd because that's a power 1. So the way this graph looks, you might want to plug in 1/2 or something. If you plug in 1/2, notice that you get something that's, let's see, 1 plus 18. That's going to give you 19. So plug in 1/2, you get something way up here. So what that means is that our graph looks like this. And due to the oddness, that. It's kind of an awkward looking graph. But getting some information from this is easier than that, and that was my point here. So get a common denominator, make one rational function. Really easy to see that we have a vertical asymptote at x equals 0. So on the y-axis, that means that we don't have a y-intercept. If you plug in 0 here, you have a problem. There's no y-intercept. There's no x-intercepts. It's easiest to see here. We have an oblique asymptote. It's easiest to see here, and then to take care of it. So that's what that graph would look like. Kind of awkward, not a lot going on with it, but hopefully it's still interesting to you. The last one, can you take and find a function from a graph? Yeah, and honestly, it's not all that bad. We just have to put a couple notes on here and then we're good to go. So when you're doing this, when you're asked to do this, take a look for some important pieces of information. Any asymptote and any x-intercept, and put odd or even on its multiplicity, as far as multiplicity. So let's take a look at our x-intercepts first. So I see 2 x-intercepts. One is at 3, and that is a cross. So I'm going to put cross. What we know is that crosses have odd multiplicity. I'm going to look at -1. Oh, that's a bounce. And what we know about bounces is they have even multiplicity. That's what you're looking for. Now we take a look at our vertical asymptote. We have one here, we have one here. This has opposite infinity, so I know that at x equals -3, I have an odd vertical asymptote. And at x equals 1, I have the same infinities. That means at x equals 1, I have an even vertical asymptote. I'm looking for my y-intercept. I see it there. I'm also looking for a horizontal asymptote. I see one at y equals 2. We'll talk about how to deal with this. So when we come up with a function, here's what to do. First, start off with your x-intercepts and your vertical asymptotes and put them in the appropriate numerator or denominator. X-intercepts come from the numerator, so they're going to give you factors on the numerator. Just match up the multiplicity. So I know that we have an x minus 3. Remember, x equals 3 would be a 0. So x minus 3 would equal 0, and that would give us a factor. This is kind of, we've done this before, going from zeros to polynomial functions. We've done that. That's why this is here. So we would have one factor, x minus 3. Because that's a cross, I know that we have a power 1. The next thing we're going to do, we're going to understand that x equals -1 would be a 0. So x plus 1 equaling 0 would be a factor for us. But because that's a balance, that has an even multiplicity, so give it a power 2, not 4 or something. We talked about why that was in another video, but we don't want to go super high, and we could put a 3, but it's probably not the case. Now go with your vertical asymptote. So I have one at -3. So if our denominator is equaling, at x equals -3, some sort of vertical asymptote, then x plus 3 would be a factor on my denominator. So x-intercepts, numerator, vertical asymptotes came from denominator. Therefore, vertical asymptotes will give you factors on the denominator. One of them is x plus 3. X plus 3, notice if that was there, that would give you an x minus 3. It has an odd multiplicity because of the opposite infinity, so we're going to put a 1. And now we have x equals 1. That was a vertical asymptote. So x minus 1 equaling 0 would be a factor on the denominator that's giving us that vertical asymptote. Hopefully at this point you're understanding we're just going backwards, but we're just kind of going in a totally opposite order also. So we're dealing with our x-intercepts before our vertical asymptotes, getting numerator before denominator, and now we're dealing with our multiplicity. So an even multiplicity for our asymptote right here, same infinity, says let's put a 2. We're almost done. The only thing that we have to do now is check for our horizontal asymptote. Our horizontal asymptote is 2. Now, what's that mean? A horizontal asymptote only happens at a constant if your degree is the same for the numerator and denominator. Let's check that. Here's 1, 2, 3, 1, 2, 3. So I know my degrees are the same here as they had to be to give me a horizontal asymptote that was not 0 and not some other end behavior. So that had to happen. Our degrees had to match up on numerator and denominator. Now, I know that horizontal asymptote is at 2. So what I'm going to do is I'm going to say, hey, this would give us 1 over 1. I'm going to make sure it's 2 over 1. I'm just going to put a 2 right there. And you can double check everything about it, but this will be this graph. I know my degrees match. I know I have a horizontal asymptote at 2. You can fake distribute to try that out. I have my vertical asymptotes at -3 odd. Cool. Positive 1 even. Got it. I have a cross at 3. I've got a bounce at -1. And my y-intercept of -2, we can plug in 2 to check that, or plug in 0 and check that if we want to. So if we did that, this would be 1, this would be -3, and this would be 2. So that would be -6 over, plugging in 0 here, 1 times 3, that would be 3. -6 divided by 3 is -2. So we know we're right on the money. So that's really nice. You can do the horizontal asymptote a slightly different way by taking this point that's not on your x-axis and calling this A. Let me show that to you now. If you called that A, then what you could do is plug in 0, -2. 0 for your x and -2 for your f of x, and it would solve that for you. And we get a equals 2, and that would tell us, hey, that a right there, that's 2. So there's a couple ways to think about that. One is just using your horizontal asymptote and you're good to go. The other one is using a point off of your x-axis and doing what I did here. We've actually done that already. We did that in our polynomials when we were in the same section as using graphs to figure out your function. So taking x-intercepts and going backwards. So we've done that. This is just another iteration with rationals. I hope all this makes sense. I hope it's gelling together. I hope that you understand the interplay between your vertical asymptote and your graph and your x-intercepts, your bounces, your crosses, putting everything together right now for you. So I know it was a long video. I hope that you hung out the whole time or watched it over several occasions or put it on 2 times speed so I talk super quick. That's fine too. Ultimately, I hope that you've enjoyed the graphing. We're basically done. This is it. This is as much as I can teach you as far as graphing rationals in this class. Next, what we're going to do, we're going to talk about inequalities for polynomials and for rationals, and we're about done. Then we wanted something completely different, talking about exponentials and logarithms. So I hope you're hanging with me. Hope you're enjoying the class still. See you later.